Welcome to Inheritance and Encapsulation. These are two fundamental pillars of object-oriented programming. Inheritance lets you reuse code by creating new classes from existing ones. Encapsulation protects your data by controlling how it's accessed and modified. Together, they make your code more maintainable, secure, and professional. Inheritance is a mechanism that allows you to create a new class based on an existing class. The new class inherits attributes and methods from the existing class, and can add its own unique features. Think of it as a parent passing traits to their children. Think of a family tree. The parent has certain traits like eyes and hair. The children inherit these traits automatically. But each child can also add their own unique characteristics. Child 1 adds a smile. Child 2 adds glasses. In programming, inheritance works the same way. The child class gets everything from the parent and can add or modify as needed. Before diving into code, let's learn the proper terminology. Understanding these terms is essential for discussing and implementing inheritance effectively. The parent class, also called base class or superclass, is the class being inherited from. The child class, also called derived class or subclass, is the class that inherits. Inherited members are attributes and methods that the child automatically receives from the parent. Override means redefining a parent's method in the child class, where the child's version takes precedence. These terms are universal in object-oriented programming. Let's see how to implement inheritance in Python. The syntax is simple but powerful. You specify the parent class in parentheses after the child class name. Here's our parent class, animal. It has a name attribute and two methods. Speak and move. This is a general class that represents any animal. Now let's create specific animal types that inherit from this base class. The dog class inherits from animal by putting animal in parentheses. Inside __init__, we call super __init__, name. To initialize the parent class. This sets up the name attribute. Then we add a new breed attribute specific to dogs. We also override the speak method to make dogs bark instead of making a generic sound. Dog inherits move from animal automatically. The super function is crucial for inheritance. It gives you access to the parent class's methods without naming the parent explicitly. This is especially important in __init__ methods. Without super, the parent's __init__ is never called. So name is never set up. This causes errors. With super, __init__ name, we call the parent's initialization, properly setting up name. Then we add our own breed attribute. Super ensures the parent class is properly initialized before adding child-specific features. Always call super __init__ in your child class constructor. Let's build a complete example with multiple child classes to see inheritance in action. Our animal base class has name and age attributes, a speak method that returns a generic sound, and an info method that describes the animal. This is our foundation. The dog class inherits from animal. It adds a breed attribute, overrides speak to bark, and adds a new fetch method unique to dogs. Dogs inherit the info method from animal automatically. The cat class also inherits from animal. It adds an indoor attribute indicating if the cat lives indoors, overrides speak to meow, and adds a scratch method. Cats also inherit the info method. Multiple classes can inherit from the same parent, each with unique features. Now let's create objects from our inherited classes and see how they use both inherited and their own unique methods. We create a dog named Buddy and a cat named Whiskers. Both can use the info method inherited from animal. Both use their overridden speak methods. So Buddy barks and Whiskers meows. Each can use their unique methods. Buddy can fetch and Whiskers can scratch. This demonstrates how inheritance combines shared functionality with specialized behavior. When Python looks for a method, it follows a specific order called method resolution order. Understanding MRO helps you predict how inheritance behaves. Python searches for methods in a specific order. First, it checks the child class. If not found, it checks the parent class. Finally, it checks the object class, which all classes inherit from. When you call dog, speak, Python finds it in dog and stops searching. When you call dog.info, Python doesn't find it in dog, so it continues to animal where it finds and uses it. This is why overridden methods in child classes take precedence over parent methods. Inheritance can have multiple levels. A child can become a parent to another child, creating a hierarchy. This models real-world relationships effectively. Here we have 3 levels. Living thing is the base, defining what it means to be alive. Animal inherits from living thing and adds species and movement. Dog inherits from animal and adds breed and barking. Dog has access to methods from all 3 levels. Alive from living thing, move from animal, and bark from itself. Each level adds more specific behavior. Python provides functions to check inheritance relationships. IsInstance checks if an object is an instance of a class. IsSubclass checks if a class inherits from another. IsInstance checks the object against a class. Dog is an instance of dog, but also of animal and living thing through inheritance. It's not a cat. IsSubclass checks class relationships directly. Dog is a subclass of animal and living thing. Animal is not a subclass of dog. Interestingly, a class is considered a subclass of itself. These functions are useful for type checking and validation. Now let's explore encapsulation, the second pillar we're covering today. Encapsulation is about bundling data with methods and restricting direct access to some components. It's about data protection and hiding implementation details. Encapsulation bundles data and methods together in a class. It controls access to internal state, hides implementation details, and protects data from invalid modifications. Think of it like a capsule protecting medicine inside. The capsule controls how the medicine is released. Similarly, encapsulation controls how data is accessed and modified, ensuring integrity and security. Python uses naming conventions to indicate access levels. Unlike some languages, Python doesn't enforce strict access control, but conventions signal intent to developers. Public attributes have no underscore and are freely accessible from anywhere. Protected attributes have one underscore, signaling they're for internal use only. Private attributes have 2 underscores, triggering name mangling to make them harder to access from outside. Remember, these are conventions. Python trusts developers to follow them, but doesn't strictly enforce access restrictions. The culture is, we're all consenting adults here. Public attributes are the default in Python. They're meant to be accessed and modified freely. Use public attributes for data that's part of the class's public interface. Public attributes like name and age can be accessed and modified directly. You can read them, change them, and use them freely. This is appropriate when there's no need for validation or when you want a simple, straightforward interface. Public attributes make up the class's public API. Protected attributes use a single underscore prefix. This is a convention telling other developers, this is internal. Don't use it directly. It's not enforced, but respected programmers follow it. Protected attributes like underscore balance and underscore transaction signal internal implementation details. Users should access balance through get underscore balance. Not directly. You can still access underscore balance directly. But the underscore warns. This is internal. It might change. Don't rely on it. Protected attributes are common in base classes meant to be subclassed, where child classes need access but external code shouldn't touch them. Private attributes use two underscores. Python applies name mangling, transforming the name to make it harder to access from outside. This provides stronger encapsulation. The underscore password attribute is private. Accessing account underscore password directly raises an attribute error. You must use verify underscore password and change underscore password methods. Python achieves this through name mangling. Internally renaming underscore password to underscore secure account underscore password. You can still access it with the mangled name. But this clearly signals you're breaking encapsulation. Private attributes are for truly sensitive data that must not be accessed directly. Getters and setters are methods that control access to attributes. Getters retrieve values. Setters modify them with validation. This is classic encapsulation. Getters like get underscore name and get underscore salary provide controlled access to protected attributes. Setters like set underscore name and set underscore salary allow modification but with validation. Set underscore salary ensures salary can't be negative. Set underscore name ensures name isn't empty. This prevents invalid data from corrupting the object state. Getters and setters are the classic encapsulation pattern. Using getters and setters provides controlled access. Get underscore salary reads the value. Set underscore salary modifies it with validation. Attempting to set a negative salary raises value error. Protecting data integrity. This pattern ensures objects maintain valid states throughout their lifetime. Python's property decorator provides a more elegant way to implement getters and setters. Properties let you access methods like attributes while maintaining control and validation. @property decorator turns a method into a getter. @name.setter creates the corresponding setter. This gives you the convenience of attribute access with the power of methods. You get validation and control while maintaining clean Pythonic syntax. Properties are the preferred Python way to implement encapsulation. Properties provide attribute-like syntax while running methods behind the scenes. This is elegant and Pythonic. With properties, you access EMP salary like a normal attribute. But it runs the getter method. You assign EMP salary equals 55,000 like a normal attribute. But it runs the setter with validation. Invalid values are caught automatically. Compare this to method syntax. Get underscore salary and set underscore salary versus simple salary access. Properties provide cleaner syntax while maintaining full control. This is why properties are the Pythonic approach to encapsulation. You can create read-only properties by defining only a getter without a setter. This is perfect for computed values or attributes that shouldn't be modified. Radius has both getter and setter, so it can be read and modified. Area and circumference have only getters, making them read-only. They're computed from radius automatically. This prevents users from setting area directly, which wouldn't make sense. Read-only properties are perfect for derived values that should be calculated, not set. You can read radius, area, and circumference. Modifying radius automatically updates the computed properties. Attempting to set area directly raises attribute error because it has no setter. Read-only properties ensure derived values stay consistent with their source data. They're computed on demand, always giving current values. Inheritance and encapsulation work together beautifully. Protected attributes allow child classes to access parent data while keeping it hidden from external code. Let's see this powerful combination. Bank account uses protected attributes _balance and _transactions. The balance property provides controlled read access. _add _transaction is protected, meant for internal use in child classes. Savings account inherits and can access _balance and _add transaction for calculating and recording. Interest external code cannot directly modify _balance, but child classes can. This combines inheritance's code reuse with encapsulation's data protection. Let's build a complete employee management system demonstrating inheritance and encapsulation working together in a practical scenario. Our employee base class encapsulates employee data with protected attributes. Properties provide read-only access to name, ID, and base salary. Calculate _salary is meant to be overridden by child classes for different employee types. This provides a foundation for specialization. Now let's create a manager class that inherits from employee and adds manager-specific features. Manager inherits from employee, gaining name, ID, and base salary. It adds a bonus with validation through a property setter. It has a protected team list and methods to manage it. Calculate _salary is overridden to include the bonus. This demonstrates inheritance adding specialized behavior while encapsulation protects data integrity. Let's add a developer class with different specialization, programming languages and project bonus. Developer also inherits from employee. It adds programming languages and project bonus. The languages property returns a copy, not the original list, preventing external modification. Calculate _salary factors in both language count and project bonus. Each employee type has unique salary calculation while sharing the base structure through inheritance. Now let's use our complete employee system, demonstrating how inheritance and encapsulation work together in practice. We create a manager and 2 developers, all inheriting from employee. The manager manages a team of developers. Properties provide encapsulated access to names and IDs. Each employee type calculates salary differently through method overriding. Modifications go through validated setters. This system demonstrates inheritance for code reuse and specialization, plus encapsulation for data protection and controlled access. Let's review the key benefits inheritance provides. Understanding these advantages helps you recognize when and how to use inheritance effectively. Code reuse. Write common functionality once in the parent. Specialization. Add specific features in child classes. Polymorphism. Use the same interface with different implementations. Maintainability. Changes to parent automatically propagate to children. Logical hierarchy. Model real world is a relationships naturally. These benefits make inheritance a powerful tool for organizing and structuring object-oriented code. Encapsulation provides equally important benefits. Let's explore why data protection and controlled access are crucial for robust software. Data protection prevents invalid modifications to object state. Validation ensures data integrity through setter methods. Hide implementation lets you change internal details without breaking external code. Controlled access defines a clear, documented interface. Security protects sensitive information like passwords or financial data. Together, these benefits make encapsulation essential for reliable, maintainable software. Let's examine common mistakes developers make with inheritance. Avoiding these pitfalls will make your code more robust and maintainable. Avoid hierarchies deeper than 3 or 4 levels. They become hard to understand and maintain. Always call super __init__ or parent initialization won't run. Respect Liskov substitution. Child classes should work anywhere the parent works. Don't inherit just for code reuse. Use composition if there's no true is-a relationship. Avoid tight coupling where children know too much about parent internals. These mistakes lead to brittle, hard to maintain code. Similarly, there are common pitfalls with encapsulation. Being aware of these helps you implement proper data protection. Don't over-encapsulate by making everything private. Only protect what needs protection. Return copies of mutable objects, not originals, or external code can modify internal state. Always validate input in setters to prevent invalid data. Be consistent. Similar attributes should have similar access levels. Don't break encapsulation by directly accessing private attributes with mangled names. These practices ensure proper encapsulation. A crucial design decision is choosing between inheritance and composition. Let's understand when to use each approach. Inheritance models is a relationships. A dog is an animal. A manager is an employee. Use inheritance for true specialization. When you need a shared interface, or when polymorphism is required. Composition models has a relationships. A car has an engine. A person has an address. Use composition when building objects from parts. When there's no is a relationship. Or when you need more flexibility. The general guideline. Favor composition over inheritance when in doubt. Composition is more flexible and less tightly coupled. Let's practice what you've learned with an exercise that combines inheritance and encapsulation. Build a vehicle rental system. Create a vehicle base class with protected attributes for brand, model, and daily rate. Add properties for reading these. Include a calculate_rental method. Then create car and motorcycle child classes that inherit from vehicle. Car adds number of doors and overrides rental calculation. Motorcycle adds engine cc and overrides rental calculation. Use properties for validation and implement proper encapsulation. Try it yourself before looking at the solution. Here's a complete solution demonstrating inheritance and encapsulation working together. The vehicle base class encapsulates brand, model, and daily rate as protected attributes. Properties provide read-only access. Calculate_rental validates input and calculates cost. The __str__ method provides a clean representation. This is our foundation. Car inherits from vehicle and adds number of doors. It overrides calculate_rental to add a 10% surcharge for 4-door cars. Super calls the parent's calculate_rental first. Then applies the surcharge. The __str__ method extends the parent's string representation. Motorcycle also inherits from vehicle and adds engine cc. It overrides calculate_rental with a 15% surcharge for engines over 600 cc. Each vehicle type has its own pricing logic while sharing the base structure. This demonstrates inheritance for specialization. Let's see our rental system in action with different vehicle types. We create a car and motorcycle. Properties provide encapsulated access to attributes. Each vehicle calculates rental cost according to its type-specific logic. The car applies a 4-door surcharge. The motorcycle applies a large engine surcharge. Validation catches invalid rental periods. This solution demonstrates inheritance for code reuse, encapsulation for data protection, and polymorphism for flexible behavior. Let's summarize the best practices for using inheritance and encapsulation effectively. For inheritance, always call super __init__. To initialize parent classes, keep hierarchies shallow to maintain clarity. Use inheritance only for true is relationships. Override methods carefully, ensuring child behavior makes sense. Favor composition when inheritance isn't natural. For encapsulation, use properties for controlled access. Validate data in setters. Return copies of mutable objects to prevent external modifications. Be consistent with access levels across similar attributes. Document your public interface clearly so users know what's safe to use. Let's see where inheritance and encapsulation are used in real software systems understanding. Practical applications helps you recognize when to use these concepts. Game development uses inheritance for game objects. Game object parent, character child, then player and enemy grandchildren. Health and position are encapsulated. Web frameworks inherit views, base view, then template view, then list view and detail view. Request handling is encapsulated. Database ORMs inherit from model base class for users. Products, orders, encapsulating database operations. GUI applications inherit widgets, widget base, then button, text field, label, encapsulating rendering and events. Security systems inherit user types with encapsulated permissions. These patterns appear everywhere in professional software. It's equally important to know when not to use inheritance and encapsulation. Over-engineering can make simple problems unnecessarily complex. Avoid inheritance when there's no clear relationship. If you only need a few methods, use composition or simple functions instead. Avoid inheritance if the relationship might change. It's hard to refactor. Don't create deep hierarchies. They're hard to understand. Avoid over-encapsulation in simple scripts or prototypes where complexity isn't justified. Data transfer objects don't need encapsulation. Performance-critical code might benefit from direct attribute access. Respect your team's culture. Sometimes simplicity wins. Use the right tool for each situation. Let's summarize the essential concepts you've learned about inheritance and encapsulation. Inheritance enables code reuse through shared parent functionality and specialization through child extensions. Always use super to properly call parent class methods. Encapsulation protects data integrity with controlled access through methods and properties. Properties provide Pythonic, elegant encapsulation with attribute-like syntax. Protected and private attributes are naming conventions, not strict enforcement. Inheritance and encapsulation work together. Protected attributes let children access parent data while keeping it hidden from external code. When in doubt, favor composition over inheritance for more flexibility and less coupling. Congratulations! You now understand two fundamental pillars of object-oriented programming. Inheritance lets you reuse and specialize code through class hierarchies. Encapsulation lets you protect and control data through access modifiers and properties. These concepts appear everywhere in professional software development. From web frameworks to game engines. You have the knowledge to write more organized, maintainable, and professional code. You've mastered inheritance and encapsulation. These powerful concepts will transform how you design and build software. Use inheritance to create logical hierarchies and reuse code. Use encapsulation to protect data and maintain integrity. Together, they form the foundation of professional object-oriented programming. Keep practicing, keep building, and keep learning. Thank you for joining us. And happy coding. Now go build amazing object-oriented applications.